Uh, Good evening, everyone, and welcome to the Chemical Engineering Industry Lectures. The talk for today is Carbon Performance Supply Chain Applications, and it is by Dr. Kedar Kulkarni, who is Senior Researcher and Manager at IBM Research India. And he has more than 15 years of experience in mathematical modeling and simulation and optimization and machine learning, and 40 plus international publications and 18 patents and one book. And we are honored to have you here, Dr. Kulkarni. Please go ahead and share your information with us.
Thanks, Anand. Thanks for the warm welcome, and excited to be speaking with the students and faculty of the Department of Chemical Engineering at IIT Hyderabad. Thanks for this opportunity. So the topic of my talk today is carbon performance supply chain applications. And in this talk, the outline that I'm going to follow is as follows, right? In the first part, so I'm sort of broadly breaking it into 4 parts, right? In the first part, I will try to give a quick intro about what are the kind of carbon emissions that what do I mean by carbon performance, or what is the performance in the context of, right? It is in the context of carbon emissions. Now, in terms of analysis or calculation or accounting, carbon emissions are of different kinds. And the one kind of carbon emission that is of interest to us, meaning corporate or B2B companies like IBM, is organizational carbon emissions. So what do I mean by that? What are the different emission scopes? What are the most important value chain or supply chain emissions that are of interest to us? And how does IBM's offerings help in that regard? Or how is it that we are well positioned to address those challenges? That's when I will segue that into carbon performance supply chain applications, which are the applications that we are going to be focusing on, and what is the role of the offerings that IBM has. And then we'll go into a bit of the details of the 2 problem classes of interest. One is order fulfillment optimization and inventory optimization. And as you can see, these 2 are use cases that are strongly related to the supply chain. And then in the end, time permitting, I will also try to share a demo that we recently built, a conceptual demo, which essentially tries to balance carbon awareness with climate resiliency, right? In the context of supply chain, effective supply chain decision making. So we'll see. So definitely we'll cover the first 3 points, and then depending on the time, we can go into the demo, and then we can close with Q&A, etc. That's my plan, right? So with that, let me get started. What do I mean by organizational carbon emissions, right? Essentially emissions that pertain to a given corporate organization, or rather enterprise corporate emissions, right? It's like some company uh, X, right, that is generating emissions either directly or indirectly, right? So let's say my reporting company in this schematic somewhere, bang in the middle, right? And this is the why am I saying reporting is because a company, when it figures out what are the emissions that it is generating, right, either directly or indirectly, is increasingly being expected to report those emissions to different intergovernmental international organizations, right? There are quite a few of them these days, right? The most common ones are, the CDP, or the Carbon Disclosure Project. There is TCFD, there is SASP, and there are also certain sectoral organizations, like for example, finance may have its own reporting requirements, finance sector. Then there may be heavy industries and so on. So all of this is sort of up and coming. It has not reached a steady state yet. However, for a general company which belongs to any given sector, any arbitrary sector, there are certain uh, how do I say, guidelines. There are no hard and fast rules and regulations as such, but there are guidelines that companies are expected to follow when they compute or estimate their emissions. And also there are guidelines about how they must be reporting, right? So in the context of a reporting company, a company of interest, company X, let's say, there are at least 3 kinds of emissions that are commonly referred to. Scope 1, scope 2 and scope 3, right? Scope 1 is essentially all the emissions that are direct, meaning all the emissions from all the company facilities and company assets like vehicles, equipment, etc., that the company owns, right? Those are all scope 1 emissions. And then there are scope 2 emissions. These are essentially related to purchased electricity, steam, heating and cooling for own use, right? In this case, a typical example would be, okay, company A is consuming electricity from some power plant which is burning coal, right? Now coal um, is a fossil fuel, right? And whenever you burn it, you are generating uh, GHGs, greenhouse gases. And so although the company that is consuming the electricity is not directly generating those emissions, because of it, by the virtue of the electricity consumption, emissions are being generated elsewhere, and hence those are scope 2 indirect emissions, right? And then there is the scope 3 category, which is going to be sort of interest to us in our discussion today, which is all of the emissions from upstream supply chain activities and downstream supply chain activities put together. That's what constitutes the scope 3 emissions, right? And there are some examples here. Okay, let's say you work with a transport company to send packages from location A to location B. Now you have no control over what this transportation company does, what kind of vehicles it uses, etc., etc. Let's say it's a very bad company, bad quote unquote, in the context of GHG emissions. It uses 20+ year old trucks to move stuff from A to B, and of course it will be generating a lot of emissions. Versus there is some other company, maybe it's slightly costlier, which has started using these electric vehicles that are becoming increasingly popular, right? So then how do you choose which one to go with, right? So those are the kind of considerations that will need to be made in the context of scope 3 emissions, right? With that, let me also give you an idea of what is the typical split, right, between scope 1, scope 2 and scope 3 emissions of a given corporate organization, right? So this pie chart sort of shows you what that split is. So if this is what this part of the pie is what scope 1 is, this is scope 2 is slightly higher, but look at scope 3, it's huge, isn't it? So this is an established fact. This is an estimated number, of course, right? But this is something that everybody agrees that scope 3 is often the largest source of emissions in a company's value chain. By value chain, I mean all of the upstream and downstream players put together, right? And hence, by the virtue of that, scope 3 emissions can represent the most significant opportunities to influence GHG reductions, right? However, the challenge here is that scope 3 emissions become extremely tough to estimate, right? I mean, think of a complex supply chain with too many nodes and too many edges, right? And let's say you are one of the nodes, your company is one of the nodes in that complex supply chain graph, right? Now maybe because your company is pretty good, and for whatever reasons you have information about nodes that are, let's say, one up, or two plus, two upstream, two nodes upstream and two nodes downstream, let's say. But anything beyond that is going to be extremely tough, right? Is what has been observed, right? If that is so, then you'll, the farther that you want to reach out into the supply chain, upstream or downstream, you'll essentially have to rely on estimating or making uh, trying to get an estimate of what these nodes and what these edges are, what kind of emissions they are generating, right? And the farther they are from your specific node, uh, your predictions are going to be pretty off, right? That's the sort of challenge. You don't get good scope 3 data, right? And anyway, in spite of even so, there are many carbon responsible companies, right, that are making open commitments, and they are they are making open commitments to the net zero movement, right? So a lot of companies you'll see are making these pledges that they want to become net zero by some time frame, right? For instance, Unilever says they want to become net zero by 2039, and they're already investing about 1 billion pounds, euros, sorry, in a new climate and nature fund, right? And they also have made an announcement that are going to carbon label all of their 70K products. And this is not just in the Unilever sort of comes in the FMCG sector, but there are in the chemical sector you have BASF that has also made a commitment, or in the cosmetics and personal care world, L'Oreal has also pledged something to that effect. So this is a movement that is sort of gaining momentum, and thanks to all of the action, thanks to all of the meetings, thanks to the recent COP26 that happened in Glasgow, there is a lot of political discussions happening as well, right? So with that background, let me move into this slide where I try to explain the sort of mental map that we have followed uh, to to design the work that we are doing, right? So as I move from the left to the right, right? So if I want to calculate, or if I want to go about reducing the supply chain carbon emissions, right? The first thing I need to do is to be able to estimate them, right? And to do so, we have actually developed in-house, models and calculation methods using the most popular set of guidelines that's out there, which is the greenhouse gas protocol, right? And this also requires access to some specialized emission factor databases that we do have. We definitely have access to, right? Once we have these APIs, as we call them, we can call these carbon APIs, right, under diverse scenarios, and then we can unleash the mathematical modeling and optimization way of thinking, and then we take the next steps from there, right? Now IBM has a very strong portfolio both in the asset management world as well as in the supply chain world, right? And these are the two sort of worlds that we are going to be focusing on to start with. In today's talk, I'll not be focusing so much on the asset management part of the world, but more on specifically two use cases under supply chain, like I mentioned earlier, which is order fulfillment and inventory optimization, right? And we will be talking about essentially two repeatable solution scenarios, right? The first one is as is carbon savings. The second one is explicit carbon optimization, right? When I say as is carbon savings, it essentially means the current supply chain solution is already giving you some optimal solution, right? It's giving you something. Now I just want to find out how good is it in terms of carbon as well. Currently it is being optimized purely from economic costs and economic constraints, right? But how does it look in terms of carbon? Does it look bad? Does it look good? Where is it at? And then based on that knowledge, we can go to the next step and say, hey, I want to now also explicitly want to optimize for the carbon emissions. If I do that, what impact does it have on costs? Is there a like a really tough trade-off there? If there is one, how do I navigate, how do I address that trade-off, and how do I effectively make decisions? So that's what we are going to try and address here, right? So here's a big picture overview of the two use cases or the two problem classes that we're going to take a look at, right? The first one is, which is what I'm showing on the left, is order fulfillment, right? And then there is the inventory optimization piece, and essentially an order management system or order fulfillment. The idea is to figure out which stores or which distribution centers and what carrier modes I should choose for a given order that is coming into the system. We'll go into the details in the later slides. And in the inventory optimization side of things, we want to figure out optimally how much and when to replenish inventory in a carbon aware manner, right? Now the question again is, how do I minimize these emissions in both of these cases in a way that I have a minimal impact on the costs, right? I essentially have to be able to navigate the trade-off between costs and emissions as smoothly as possible. So how do we do that, right? So let me now take a look at these things one at a time, right? So what do I mean by a carbon performant supply chain in the context of order fulfillment, right? So in a typical order management system or the order fulfillment problem, the central repository or the central database for an order fulfillment optimization problem is the order management system, right? This is the system that, oops, this is the system that receives all the orders that people place online, right? So it's like, let's say you're sitting at your home and you make an order online, right? And then this order goes to the order management system of IBM, right? And then it internally figures out, it makes a lot of these calculations, runs an algorithm, and figures out from where this order must be satisfied. And the order may also have multiple items in it, right? You can say order, a T-shirt and maybe a pair of shoes, right? Now, it's not necessary that both of these items have to come from exactly one node, right? You may also, I mean, the order management system, the optimizer part of the OMS might decide, hey, I'll send. It makes sense perfectly to send the T-shirt from node A, but the pair of shoes from node B, because that's the most cost optimal, right? Those kind of things can happen, right? Now, how does the order fulfillment optimization, current order fulfillment optimization, make these decisions? It does so by minimizing two kinds of costs, right? One is upfront costs, which includes shipping, labor, and processing costs. Meaning, once I place an order, these are costs that I will have to pay. Sorry, these are costs that I will have to bear no matter what, right? Whereas there is also the other side of costs, which is the predictive item node costs, right? These are predictive in nature, and these sort of include costs like stock out costs or markdown avoidance costs. I mean, we don't know exactly if they're going to happen in the sometime in the future, and if they do happen, we don't know what the intensity of those are going to be. So there will be a probability associated with those occurrences, and we need to account for that in our decision making as well, right? Of course, currently the optimization solution or the algorithm that we use accounts or minimizes only for the economic costs, right? It does not explicitly account for any carbon emissions, and by that we really mean only, sort of one node up or down, or whichever way you want to look at it, right? This is essentially just the transportation and distribution emissions that I'm talking about, right? Let's say that's the only scope that I'm interested in right now, right? Because that's something that I can get the data for, and I can at least attempt an optimization, right? Now, these transportation emissions, right? Like I said, any company, any retail company. So think something like Nike or Reebok or any of some favorite brand of yours, right? It'll, unless it's like a really large company conglomerate, it will not be operating its own fleet of vehicles, right? It'll say, okay, I'll do what I'm best at. Okay, let's say I know how to manufacture shoes, and once I'm done, when I get an order, I say, hey, FedEx, UPS, or whoever, please, take this package and deliver it to this address, right? In which case, me being Nike and Reebok, I'm essentially contracting, giving that responsibility to FedEx and UPS, and hence they are my, you know downstream partners in the supply chain, and the emissions that they will generate because of transportation and distribution will be attributed to me as a scope 3 emission, right? So the decisions that I make, who I choose to work with, etc., will also be can be influenced to consider working with those partners that will not have very high scope 3 emissions, right? So so the carbon performance order fulfillment, um, in principle, would optimally balance the economic costs of order fulfillment with carbon emissions. And how does it do that? So before we go into the details of that, maybe I want to give you a quick, uh, you know, this is a screenshot of the demo that we had built. This is not a, I'm not going to go into the full-fledged demo for this part. All right, this is a demo that we had built that addresses the first of the two repeatable scenarios that I spoke about. It. The first one was as is savings, and the second one was explicit carbon optimization. So this is the one about as is savings. Right, this is a demo that we had built about a year ago. About a year ago, where we sort of give a we compute the numbers and we show it in a UI exactly what these numbers look like. Okay, so what is this demo all about, right? So this is actually realistic client data. It's not exactly, the numbers are not exact, of course, but this is for a period of 15th April to 2019 to 31st May 2019. This is about 45 days, right? Now this is for a retail company that is getting orders over these 45 days, right? And these orders, these come into the system pretty fast, right? You can get hundreds of orders in a second depending on what the load or which kind of time frame you are at, right? I mean, of course, there will be peaks and lows depending on what time of the day, which day of the week, is there a holiday, blah blah blah, all those things of course matter. But over a period of 45 days, all of these orders that are coming in, sequentially in time, are optimized in real time to figure out where they should be procured from, or where procured from, or where they should be fulfilled from, right? Which node, which carrier mode, etc., etc., right? And all of that, the optimized solution that is generated by the Sterling fulfillment optimizer, which is IBM's flagship product, is compared in terms of its it's compared with a baseline, right? This baseline is a rule based heuristic, right? So by default we essentially show the monetary comparison. I'm not going to show that, but because that's by default. But what we also do in this demo is we show the sustainability comparison, which means how good is my current solution that the fulfillment optimizer is generating, how good is that in comparison to the baseline, right? So as you can see here, the purple one is what is generated after optimization, meaning after the fulfillment optimization has done its job of optimizing rigorously. And then the green one is the no optimization uh, line, right? This is the one that uses the rule based heuristic, right? And as you can see, the green line is always above the purple line, which means the purple line is pretty good in terms of the emissions. What I have on the y-axis is essentially the emissions, right? And what does it really look like in terms of the total emissions that is saved over 45 days? It looks like about 122 tons of carbon dioxide reduced, right? Which is equivalent to about 730 trees, and which is also equivalent to about 182 uh, New York City to Paris air trips, right? So we essentially ended up reducing so much without really doing much about explicitly optimizing the emissions, right? Which means if I try to explicitly optimize for the emissions, maybe I can achieve more, maybe not, I don't know, right? But there is definitely potential, right? And this graph essentially shows where exactly the reduction came about. Where did it? I mean, you say there is a reduction. Where exactly is the reduction? The reduction is largely because of a reduction in air transport, right? And because certain orders that were fulfilled earlier through air are now being fulfilled through rail or through road, the emission has reduced considerably. And understandably, the reduction in air transport has increased the amount of ground transport, right? However, this graph is in terms of not the number of orders, right? It's in terms of the amount of carbon dioxide. And this graph immediately suggests that air transport is at least about 5 times as intensive as ground transport, which means one package that was, if I move it through road transport from A to B, and the emission is X units. If I do the same with air, the emission will be about 5x units, right? Of course, there are other considerations. It's not as straightforward as that. If the customer is saying, "Hey, I don't care. I just need it to be delivered tomorrow," and the only place that he can get it from is 2,000 miles away, you'll have to fly it down, right? There is no option to that. But the idea here is, while I respect those constraints, is there anything that I can do? And looks like we can do, which means the baseline, being a pure rule based heuristic, is not able to do a good job, right? Now, with that, let me go into the next part where I talk about the explicit carbon optimization. I'll not be able to go into the details of the algorithm and exactly what we do, but to give you an overview, so here's what we did, right? In the earlier graph, you saw that we plotted the total emissions of the rule-based approach versus the rigorous optimization approach, right? That was a daily number that we plotted for those 45 days. But the other question is, what does it look like when I compare the baseline with the rigorous optimization solution order by order, right? Because it's actually the order by order thing that should also be important, right? So when we do that, when I plot the total number of orders versus time, right, day 1 to day 40, right? This is for a different retailer, so it's not exactly the same data as we saw in the earlier one. But if I plot the total number of orders over these 40 days, right, so each day has so many orders, right? Now I want to figure out in terms of the comparison between the baseline and the rigorous optimization approach, what do the orders look like? How many of the orders are lower emission orders, right? how many of the rigorously optimized orders have lower emissions than the baseline, how many of them have higher emissions than the baseline, right? Now, if the rigorously optimized orders, by definition, they already have a lower costs than the baseline, so cost wise we are covered. But if they are also lower emission, that means we are covered emission wise as well, right? And hence I can sort of grade out and say, okay, this is an already addressed class of orders, I need not bother about it. However, there is a class of there's a number of these higher emission orders shown in red, where these orders, by definition, because these are done through rigorous optimization and because they have been checked, the costs that they generate are lower than the baseline. All right, but they seem to have higher emissions than baseline, which we thought was sort of interesting. And the reason behind that is because of package consolidation, right? It's quite possible that you may make an order which has two items in it. Like let's say that we take the same example. I order for a t-shirt and I order for a pair of shoes, right? Now, if these two are easy to procure from some place that is close by, then of course the system will go ahead and okay, just send it from that place, right? But let's say we don't have both of these in the closest location, right? So what does the algorithm do? It splits it out, right? And it says, okay, I don't have both of them in the same location, but I have one I have the pair of shoes in one location which is decently close, and I also have the t-shirt which is in a location that's decently close. Okay, so good. So I sent these two packages. Now the moment I sent two packages versus one package, the shipping cost goes up, the economic cost goes up. So the moment if I ignore the emission aspect for the time being, right, the solution will not consider taking these two options, right? It will not consider getting the packages delivered from two different nodes. It will try as much as possible to deliver it from a single node, and it may end up getting a node which is much farther out in terms of distance, right, and deliver it from there, because it will be sending it essentially in the same package, right? So it is that dynamic that sort of seems to affect or seem to cause what we see here, right? And we essentially see that there is about 25% of the orders that are fulfilled that were fulfilled based on purely economic metrics have higher emissions than the baseline. This is the red part, right? Now the carbon performance fulfillment optimizer in principle would balance these economic costs against the carbon emissions in a rigorous manner, right? This is a carbon constraint approach, or we can take the other approach of assigning upfront dollar costs for emissions, etc. That's also a possibility. And this is the overall algorithmic chart or schematic, right, that we sort of follow. It essentially boils down to a multi-objective order fulfillment optimization problem, where we are essentially balancing these economic costs against emissions. And the carbon emissions, like I said, the kind of carbon emissions that we are considering can be estimated using some of the models that the GHG protocol recommends. But at the same time, we are considering a different bunch of costs. We consider the shipping cost, we consider the node load balancing cost, right? Then we also talked about markdown avoidance and stock out costs being predictive item node costs, and then we also want to reduce the labor costs, right? So this is essentially trying to give you an overview of the solution approach. Unfortunately, I cannot go into the details of the approach or the results, because it's sort of we are filing a couple of IPs on that, and we are also writing a couple of papers on that. But I hope to be able to present that soon, maybe in the near future. Okay, with that, let me move into the inventory optimization piece. I don't know how many of us here are aware of the inventory optimization piece, but maybe a quick intro. All right, so let's say I plot the inventory position of an item over time as it gets consumed by demand, right, and also as it gets replenished based on whatever you get from your suppliers based on the orders that you make, right? And it has a zigzag fashion in which it varies over time. And this is the classic problem called the EOQ, economic order quantity problem, has been studied for a long time. I think the first paper on it came in the 60s or 70s. There have been lots of variants of that problem, but to this day, it in practice it remains the the heart of all inventory optimization problems, right? So the idea here is, as the inventory reduces and increases because of replenishment over time, there are certain things that you want to do optimally in the system. And what is that? So conceptually, it is, when do I want to order an inventory? When do I want to order a set of items, right? And how much? These are the two extremely important decisions that you want to take. And these are essentially the reorder point and the reorder quantity. At the reorder point is that line, horizontal line below which, when you see your inventories has gone, you want to make an order, you want to place an order, right? And the reorder quantity is the moment it has gone below ROP, you want to figure out how much to order. Because whenever you make an order, in a real world, it will take a finite amount of time for you to get that order delivered, right? Which means I need to order before, a lot before the amount of inventory goes to zero, right? And that's where the math comes in. Okay, if I'm ordering from a very far off place, then I need to order much in advance, right? On the other hand, if I can get it from a place which is just within town, then it doesn't matter. I did not keep too much inventory, right? Perhaps those kind of things will start mattering. And these, whatever I explained verbally, is essentially formulated mathematically, and you're essentially optimizing, you're solving an optimization problem where you have upfront costs, right, which essentially include the replenishment cost, meaning whenever you place an order, what's the amount of cost that you bear. And once you have those have been delivered, it's not as if you just get them delivered and they get consumed by demand, right? You'll have to store them somewhere, which means you'll have to hold them. And then there are holding costs. If you are keeping it in a warehouse, you'll need to pay rent. If I want to keep 100,000 units in a warehouse, the holding costs can be significant, right? But at the same time, we also typically consider some predictive item costs, which is that of stock out. So what do you mean by stock out, right? Stock out is essentially an event where a particular item is in demand, but you just don't have enough items. Uh, mm, uh, you don't have enough units of that item, right? Let's say you want a pair of shoes, right? A specific pair of shoes, and there is a demand for 100 units, but you have only 70, so you are falling short of 30. Right now, this may be a bit of a put off for the customer, right? And there is a cost that you sort of bear. In some cases, it's also possible that these stock out costs can be computed a lot more accurately as well, especially if they have implications in terms of expedited delivery. Maybe the agreement between the client and supplier demands that if the supplier is falling short of X items, then you have to expeditedly deliver them, right? So then it becomes obvious what those costs are, etc. And then there are certain service level constraints that are agreed upon, meaning if I have asked for 100 items overall, then at any given point in time, the supplier should be giving me at least 98, and that is a 98% service level, right? Of course, all of this optimization only accounts for the economic costs purely, and like earlier, it does not account for any transportation and distribution emissions, right? And also, if there is an expedited delivery, in the case of a stock out, there will also be emissions there. So those are not being accounted for currently, right? And typically, given that we will be working with other entities in the supply chain, and we are essentially doing what we are known for, right? Meaning, if I am a shoemaking company, then I'm not really doing transport, etc. With those assumptions, we can say that most of these emissions can be categorized as scope 3 emissions, right? So how does this optimization problem look like for how do these optimization problems compare, right, between the cost only approach and the emission only approach? So what you see here on the left is the cost only approach, and this is the current approach that most inventory optimization solvers use, right? You're essentially trying to some this or some variant thereof, but the basic idea is that you want to minimize some of the ordering, holding, and stock out costs, or in general the predictive costs. You subject them to some service level constraints, and these are parameterized by cost, usage, and lead time parameters, right? Now, if I look at the pure emission only optimization, right, meaning I totally disregard costs. If I look at it purely from the emissions perspective, then I get a philosophically similar problem structure where I say, okay, Instead of costs, now I'm minimizing the ordering emissions, the holding emissions, and the stock out emissions, meaning the sum of these three, right? Subject to the same service level constraint as earlier, but now we are parameterized by a slightly different set of parameters. I need to know what's the transportation mode. I need to know what's the distance. I need to know where the warehouse is. I need to know what are the item specs, right? I need to know certain usage and lead time parameters, right? Once I know all of these, I will be able to compute my ordering and stock out emissions, right? Because essentially whenever I order something, it will be delivered to me using some vehicle, right, which will have some transportation mode, right, oops which will have some transportation mode which will be, you know done over a distance, right? So I will essentially need to get access to all of that, right? And in terms of holding emissions, I will need to know where these items are being stored. If it is being stored at a warehouse, which is the grid that is supplying electricity to this warehouse, right? Is this a relatively green grid, meaning is it the kind that supplies 60% based 60% electricity coming from renewable and 40 coming from fossil, or what is that mix, what is that looking like? Because that will sort of determine how much emissions you need to be attributing to what you keep in the warehouse, right? It's not as if the items by themselves are generating these emissions, but because there are items, there will be human activity, there will be vehicles out there, right? There will be electricity that gets spent. uh, and in the case of refrigeration, I think because it becomes even a lot clearer, right? Because I'll be consuming more electricity, and there will be other greenhouse gases also that I will have to perhaps worry about, because refrigeration requires these refrigerants which are pretty bad GHGs, right? So with these in mind, again, if I look at the two problem classes, one is as is carbon savings, where I essentially get a delta of between the total emissions for the current solution, and the current solution is something that I have optimized rigorously based on these the cost only approach, and this minus the total emissions for some baseline, right? Now this baseline is essentially an example of that would be you run this optimization every every delta t, every some time period. Let's say you run it every 1 month, right? So whenever I run it after a month, right, the optimal solution that I had obtained 1 month ago, right, becomes my baseline, and whatever I get now, because I'm running the optimization now, becomes my current solution, right? So the total emissions for the current solution minus that for the baseline is essentially what as is carbon savings looks like, right? And then there is the other approach where we try to balance, right, the emissions with the costs, right, which is what the right hand side of this slide talks about. Let's go to that slightly later, but first look at this part, these two essentially, right? So I'm trying to show you what this as is savings looks like, right? So what we did was we considered just focus on this table for just some time, right? What we did here was we tried to compute the as is savings for some based on some representative data for some set of items, right, inventory items, and we computed what the yearly economic costs and what the yearly emissions look like for the baseline, meaning this is for the solution that was optimal purely from the cost perspective. All right, this was optimal purely from the cost perspective about a month ago, right? And now in the current month, when I again rerun this optimization, this is again pure cost only optimization. I'm not accounting for the emissions explicitly yet, right? So in that case, this is what the solution looks like, right? Cost only optimization current. This is what the economic costs look like, and these are the yearly emissions that are evaluated. These are not optimal, right? Because there is only optimization that's happening for the cost, right? With these as references, you see that you're saving money, you're saving like 3.9% costs, and you're also saving emissions, right? So this is your as is savings approach. Now what happens if I try to explicitly optimize for my carbon, right? So again, here this is going to be a multi-objective optimization problem, like I mentioned, right? With one end of the spectrum being a pure cost only optimization, right, which is the one in red here, and the other end of the spectrum is a pure emission only optimization, which is the one in green or whatever that color is, cyan, yeah, right? Oops. So, and between these two is where the entire Pareto lies, the Pareto front, right? So the closer a point on this Pareto is to the only cost solution, the weightage for the cost is higher, and the closer this point is to the pure emission only solution, the weightage for emissions is higher, right? Now, what do these, you know, extremities look like, right? What, how does the cost only optimization correspond, compare with the emission only optimization? Well, we see that as expected, there is an increase in costs, right? I mean, there is a negative savings increase indicates an increase in costs, right? Which means if I want to purely reduce my emissions, I'll have to pay up essentially, right? Of course, the yearly emissions will reduce, right? It reduces in this case by about 17%. But the point to note, the most important point to note is that it is possible to significantly reduce my carbon, right, with a modest increase in costs. Now, that's the attractive feature that we have latched on, and there is a mathematical property there which allows us to do that. Because of the mathematical properties of the functions that we work with, this is what happens, and this is something that people have conjectured. This is something that people have written papers on. There's also IP on this and so on. So in this case, the claim here is, or our observation is, that we can reduce emissions significantly, in this case 17%, with only a very small increase in costs, right? And again, there is a lot of work that's happening on this as we speak, and I really hope I can share some more results on this maybe in a future talk. But that's essentially what I had until this part of the talk, after which I was planning to go into the conceptual demo that I referred to. So how are we doing with respect to time, Anand?
See, I mean, we started only at 4:15.
Okay.
So, you're 40 minutes into your talk.
Mm-hmm.
So, you can take 10 more minutes if you would
Okay.
like.
Yes, I don't think I'll require anything more than that. Okay. You can see my full screen, right?
Now, no, but just a second ago, yes, I could see your full screen.
Oh, is it? Yeah.
I mean, whatever you were doing before, I was seeing your full screen. Now it's like, I can see it only within a tab.
Okay.
Just open the PowerPoint and then click on.
Sorry, just one sec. Yeah, no, I mean, now I just want to switch over to I want to switch over to the browser, right?
Yeah.
Can you see what I'm typing on the browser?
Yes.
Okay, cool. So this is the supply chain dashboard. This is the demo. This is the conceptual demo that we have built. All right. So here the focus is on, again, this is a work in progress. This is built based on representative data. This has not been validated yet out in the field, etc. But we did demo this already at the National Retail Federation conference in the US about a month ago. Right. So this is fresh out of the oven, so to say. Right. So the idea here is we want to enable end-to-end supply chain decision making, right, while accounting for A, economic costs, of course, B, carbon emissions, like we saw just a while ago, and C, also climate risk, right? Why are we putting these two in different categories, right? There are two methodological approaches to address climate change. One is mitigation, where we are trying to reduce the emissions in the first place. We are directly attacking at the root cause that generates global warming and all of its harmful effects, right? That's what mitigation is all about. When we reduce emissions, we are doing mitigation, right? But the other approach is adaptation, which takes a more practical approach, right? It is essentially reactive, meaning it says, okay, emissions are already out there, they are warming my planet, they are causing climatic disruptions, but now can I predict these climatic disruptions with some degree of reliability and use that to make effective decisions, right? And we want to sort of marry these two or three approaches, right? Economic costs, carbon, and climate risk, right, in the context of an end-to-end supply chain. So what we did was essentially took an example supply chain. So what we have here is an example t-shirt supply chain. And how does this decision making look like in the context of this t-shirt supply chain is what we're trying to show through the demo, right? So let's say I have this t-shirt supply chain. As you can see, it's a global t-shirt supply chain that spreads across several continents and countries, right? You have uh, let's start at the extreme right. You have some place in India, Nagpur, let's say, which sends cotton, supplies cotton, right? And then there is some place in China, Jiangxing, that is also supplying cotton. It goes to a factory in Bangladesh, right? In Bangladesh, a lot of these processing happens, right? The cotton is ginned, and then there is yarning, bleaching, cloth formation, cutting, sewing, all of that. And then these are you know packaged. The t-shirts are finally made and packaged and then sent through a ship all the way across to uh, to a warehouse somewhere in the outskirts, in upstate New York, right? Then they stay there for some time, and then finally they are transported to your brick and mortar stores, right? One in Houston, Texas, and the other one in Dallas, right? If this is your example supply chain, how does this tool help us with the visualization as well as with the decision making? Is what this demo is all about. Right now, the first thing that you can do is you can click on this node, and you can view what are the activities that this particular node is doing. What does its carbon footprint look like, and what are the climate risks? So, for instance, in this case, the biggest climate risk is that of water availability. This is at place in Bangladesh, and carbon footprint looks like this carbon footprint is about 87%, which is pretty huge. 87% of the entire end-to-end supply chain carbon footprint, right? If I click on view, I can get more information about the timelines, right? How does the climate risk look like as a function of time, right? And again, this way we can also do the carbon footprint overview. This shows me over as a function of time what my carbon emissions look like. Both the target carbon footprint, which is something that we use as an input, and the projected carbon footprint, right? So in that fashion, you can click on all of these nodes and you can get all of this information. You can do the same for the edges also. So if I click on the longest edge, right, I get information, the same kind of information. What's the carbon footprint? What are the risks, etc. If I click on view, I get all information. What is the mode of transport? What is the distance? What are the climatic risk overview? What is the carbon footprint overview, etc., etc. Right. So this is the input that we have given to the system, and this is the climatic risk overview, right, where we have all of the locations on the y-axis, locations of interest in this end-to-end supply chain on the y-axis, and versus time, right? And these different colors correspond to different kinds of climatic risks, and you can see that the risks increase and decrease over time, right? So the darker hue indicates basically a higher intensity of that risk, and lighter hue indicates a lower intensity of that risk. I mean, if it is white, that means the risk is very, very low, right? So you can see these spots, like they increase and decrease over time. And in Dhaka, as we had seen, like we just see the water availability problem sort of peaking somewhere here, here, and here, right? And then we have the carbon footprint overview for the entire supply chain, right? This is the pie chart showing the distribution. This is the overall time series distribution. You can see that the projected carbon footprint, which is in light green, is much larger than uh, the dark green, which is the target carbon footprint, which means there is some optimization that needs to be done here. So, and we need to be able to do that while not affecting the costs too much, and also while being cognizant of the climate risk. So how to do that? That's when we click on explore, right? And this is again the overall view. Okay, we see that there is the capacity fulfillment is only about 85.5%, right? Uh, which is we need to be able to do better than that. The overall climate risk is high, and this is the carbon footprint for 4,000 t-shirts. The total target carbon footprint is 21.3 million kg carbon dioxide, but the projected one is 21.9. So there is a big difference here, which means we need to be able to do better, right? So I go down and then I click here. Uh, this is where essentially I'm going closer to the optimization that we carry out. So let's say I want to optimize my costs, my carbon emissions, and impact of climate risk over, I don't know, April to September. Yeah, let's do April to September. April to September. Yeah, and okay, here's what it is like. And then when I click on optimize, and then what it essentially shows is the different kinds of solutions that are generated on the Pareto, right? The Pareto between the costs, emissions, and the climate risk, right? But to sort of let the business user, quickly navigate this, there are options like, okay, do you want alternative suppliers or not? I'll say yes. Then that will move my options around a bit. What is your climatic risk of appetite? Let's say it's low, right? And let's say my carbon excuse me, my carbon footprint sensitivity is, let's say, high, right? Cost sensitivity, I don't know, mid, or yeah, mid. All right. So you see that these options sort of move around. And what are these options? So just to give you a quick explanation. So what you see in dark green in this big circle is your current option. This is where your supply chain is operating at in terms of its operational decisions, right? And these three smaller circles that have been generated are generated from the optimization that is, working under the hood, right? Now, on the y-axis, you have the carbon footprint. On the x-axis, you have the costs, and the size of the circle indicates the amount of climate risk, right? So, so in a theoretically ideal scenario, you would want to have a very, very small circle at the origin, right? Because essentially very small, close to the origin, right? Very small carbon footprint, very small costs, and very small climate risk. This is just to give you a perspective, right? And of course, you can see that there are these three options that are essentially, laid almost like how they would be laid on a Pareto, right? Now, if I look at these two options, right, these two are certainly better than my dark green, right? Why? A, because they are smaller circles, which means they are smaller in risk, and B, because they are closer to the origin, which means they are smaller in terms of costs as well as carbon footprint, right? If I look at this one, this is also good in terms of my climate risk, right? It's a smaller circle, but the cost is huge, right? Yes, it gives me a decent reduction in carbon footprint, but the cost is huge, right? What does this look like? This is my option 3. So if I look at option 3, look at this. The carbon footprint change is, my footprint changes, reduces by 67%, but my cost increases by 34%. That's huge, right? So the competition is really between option 1 and option 2 because they're pretty close to each other, right? Now, what does option 2 look like? Okay, reduction in carbon footprint by 28%, cost decreases by 25%. What does it look like for option 1? Okay, the cost change is lower here, right? And the carbon footprint is also decent enough. Okay, so let's go with option 1, and I say save, right? Once I say save, it goes back to the same place here. It says, okay, you can see that the capacity fulfillment has increased. Earlier it was 85.5, now it has become 87.6. All right, and we can see that the carbon numbers have also changed, right? The target carbon footprint is now whatever 22.7, projected is around 23.3, which is still larger, but uh, well, we didn't consider the target into the optimization problem, but that's a different optimization problem altogether. But this is essentially how we would like to encourage the decision making within an entire end-to-end supply chain. So like I said, this is a work in progress, but these are some of the ideas that we recently presented at a national retail conference, and this is a sort of a conceptual demo, right? I think with that I would like to close and open it up for questions. Thanks for your attention.
Okay. Thank you, Dr. Kulkarni, for a nice talk. And I have some questions, but we are going to do the questions outside the recording.
Sure.
Okay. So I'd like to thank you for accepting our invitation. I request Professor Kishalay Mitra to say a few words of thanks to our distinguished speaker, and then we will close the recording.
Thanks so much, Dr. Kedar, for the state-of-the-art presentation. We heard about multi-objective optimization, carbon credit calculations, optimization of supply chain decision for sustainability, which I think are all need of the hour. So many of these concepts are being used in many of our research, and glad to see that our research is so connected with the need of the recent time. This is one of the purposes of this lecture series, to make our students abreast of the current happenings in the
Yeah,
industry and get ourselves updated with the current trend. And IBM being one of the leads in many industry offerings, working in real field with many other leading companies, what could have been a better opportunity to hear from. So thanks so much for sharing your experience with us, Dr. Kedar. We wish a great progress of your research in future and expect you will share the same from time to time with us in this fashion. Thanks so much.
absolutely. Thank you so much. It's been a pleasure. Thanks, Kishle.
Okay, I'll stop the recording now.